Hello. In this video, we're going to learn about modeling population migration with matrix algebra. So to begin, we're going to be modeling a simple situation. Imagine there are two different regions, and I'm not very good at naming regions, so I'll maybe name them alpha and beta. And there's some kind of population which moves back and forth between these two areas. It can be really any kind of animal you want. So for instance, maybe you've got some kind of a bird. I don't know why I'm drawing a picture of a bird, but it helps me visualize this. So we've got some birds which are moving back and forth between these two areas. Right? Some birds live in area alpha, and perhaps each year some of them migrate over to area beta, and some of them stay in area alpha, which I'll represent with an arrow pointing from alpha to itself. Similarly, each year, some of the population that's currently residing in area beta migrates to area alpha. And similarly, some of the population stays in area beta. So we have some percentages in each of these cases. So for example, maybe 10% migrates from alpha to beta every year. I'll indicate that by writing a 0.10 near that arrow. And maybe 30% of the population migrates from beta to alpha each year. We can also conclude, since 10% of the population leaves alpha, that 90% of the population stays in alpha. And similarly, in region beta, since 30% of the population leaves, that means that 70% of the population stays. We're going to create a mathematical model of this. I'm going to go to the next page, and I'm going to redraw the picture up here for convenience. We've got 10% moving from alpha to beta. Each year, 30% moving from beta to alpha, which means 90% stay in alpha and 70% stay in beta. I'm going to represent the population distribution, that is the number of birds or whatever animal you're modeling, as a vector. Right, so I'm going to think of P of t as a vector representing the populations, let's say the population distribution. This is going to be stored as a vector at time t. And so for instance, we'll think of this as the population, I'll abbreviate as pop, in area alpha. It's the first entry, and then the population in area beta as the second entry. So for example, we might say that the populations at time 0, perhaps we have 60 birds in area alpha and 80 birds in area beta. And we'd like to figure out what happens to this population every year. So for example, let's say we'd like to calculate the population 1 year later. So we can do that with some mathematical calculations. So for instance, the top entry of this vector, recall that's the population in area alpha. Now to calculate what happens next year, we know that 90% of the current population stays in that area. So that's 90% of 60, plus we'll get an influx of 30% of area beta's population, which we said that was 80. And similarly, area beta's population next year will get 10% from area alpha. So 10% of the alpha population, which is 60, plus 70% of the beta population stays put. So 70% times 80. And notice that I'm arranging these in a certain order to draw attention to the patterns we have. So if we calculate this out, we'll get 90% of 60, that's 54, plus 30% of 80, that's 24. So next year's population in area alpha is 78. Similarly, in the beta region, we'll get 10% of 60, which is 6, plus 70% of 80, which is 56, leading us to a final population of 62 in the following year. And one thing we might want to notice, it's kind of a nice, easy check. We have a constant total population. Right? In year 0, if you add together those two numbers, you might notice that the total population is 140. We should have the same population every year. Right? So as a quick check, the total in year 1 is still 140. In this particular model, all models are simplifications of some real-world phenomena, but in this population model, we're assuming nobody dies, nobody's born, just a population is moving around between two areas. And so the population remains constant at 140. What if we wanted to calculate the population at year 2? Well, we're going to carry out a similar calculation. Right? So for year 2, 90% of the population in area alpha stays. So this time we'll multiply 0.90 times the population in year 1, which was 78. We also get an influx of 30% from area beta, which in the previous year was 62. Then to calculate year 2's beta population, we get an influx of 10% from region alpha, plus 70% stays put in region beta. Now this time, you might notice that the values are not going to be whole numbers, which presents a problem because you can't really have a fraction of a bird migrating from one region to another. So instead, we'll just think of this as an approximation. Right? And I did the math on a calculator in this case. The new population in alpha is approximately 88.8, and the new population in beta is 51.2. And so we could continue this process to figure out the population years 3 and 4 and so forth. I'd rather not continue to multiply out the population by hand. One question we're going to ask ourselves is, what's the long-term population? After 10 years, after 20 years, does the population in each area settle down? Does it kind of level out to a constant number? Does it continue to fluctuate between different numbers? Right now, it seems like the alpha population continues to grow and the beta population continues to shrink. Will all the birds eventually migrate to alpha? These are some of the questions we're going to use matrix algebra to help us calculate. But first, let's take the pattern of these calculations and write it in more general terms using a matrix. So moving on to the next page. To calculate the population in any particular year, say the population in year t, think of it as if t is the present, so this year's population. Right? We did a certain pattern of multiplication. In fact, those dot products, right, that looks like a dot product calculation in the previous year. Right? We have a product plus a product in each case. So we can think of this calculation as a matrix multiplication. Right? So 0.90, 0.30, 0.10, and 0.70, we took those values and we multiplied it by the vector of populations from the previous year. And we can think of P of t minus 1 as last year's population vector. And that's the procedure for going from one year to the next. Or if you prefer, you can think of it in equivalent terms as the population at time t plus 1. Think of that as next year's population. And you can calculate next year if you know this year. Again, multiplying by the same matrix. Right, next year's population can be thought of as this matrix times the vector which stores this year's population. And the takeaway from this is to calculate the change in population from one year to the next, we're really performing a matrix multiplication. And to make the math a little bit simpler, I'd like to think of this matrix with these values in it as the migration matrix. And so in this case, we have 0.90, 0.30, 0.10, and 0.70. I'd like to think of this as a migration matrix. It gives us the percentages of the population which move from region to region. In general, this matrix will have the form A, B, C, D, and these values represent moving from, say, area alpha or area beta, moving from those areas to alpha into beta. And one of the patterns I would like to call your attention to is that since no members of the population are born or die, we have to account for a full 100% of the population in each region. And so, for instance, you might have noticed that the numbers in the first column add to 100%. The numbers in the second column add to 100%, right? And that will always be true. Right, so the columns add to 100%. You can think of the number 1 as representing that. And so just something to notice when we write that out. Okay, so with this notation in hand, we can more easily write what we're calculating. And so the population in year t plus 1, we can think of that as the migration matrix times the population in year t. So what if we wanted to calculate something like the population in year 3? Well, according to this formula, we could write that as m times the population in year 2. Then you might ask yourself, well, how would you calculate the population in year 2? Well, by applying the same formula again, the population in year 2 is the migration matrix times the population in year 1. And you could keep asking yourself this question, right? How do I calculate the population in year 1? It's the migration matrix times the population in year 0, which is usually our initial condition. But if we rewrite this, we have the matrix M multiplied by itself 3 times. Right, so to calculate the population in year 3, that's the same thing as starting with your initial population, the population at time 0, and multiplying it by m cubed. And this pattern just will hold in general. So in general, what do we have? We have that the population in year t, we can think of that as m to the tth power times the initial population. And I like to think of p of 0 as when time starts. Initial population. And so one question we might ask ourselves is the following. The big question is, what is the long-term population distribution? In other words, does it level out? Does it oscillate? In kind of calculus-related terms, you could even write it like this. As time gets larger and larger, as time approaches infinity, what happens to P of t? Right, this is the question we'd like to answer. But in order to answer this, it would help to have a way to calculate powers of a matrix. Fortunately, using some techniques that you've learned previously, such as calculating eigenvalues and eigenvectors and using them to diagonalize a matrix, we'll be able to answer this question. So returning to our example from before, right, the original example, the migration matrix M was 0.90, 0.30, 0.10, and 0.70. We're going to go ahead and diagonalize this matrix, which first requires us to find the eigenvalues and eigenvectors. So eigenvalues and eigenvectors. And so first we have to calculate the characteristic polynomial. Right, we're going to find the determinant of this matrix minus lambda times I and set that equal to 0. And so we'd like the determinant of 0.90 minus lambda, 0.30, 0.10, 0.70 minus lambda. And that determinant is 0.90 minus lambda times 0.70 minus lambda minus 0.10 times 0.30. And what do we get here? Let's see, we'll get 0.90 times 0.70. And that's going to be 0.63. See, we have a minus 0.9 lambda minus 0.7 lambda plus lambda squared minus 0.10 times 0.30. Right? That's going to be 0.3333. Wait, no, that would be division. 0.10 times 0.30 is 0.30. 0.03, sorry, a tenth of 0.30. Ooh. Right, gathering like terms, we're going to have lambda squared minus 1.6 lambda. Then combining the constant terms, we have plus, all right, this is 0.6. And we're going to set this equal to 0 and solve for those eigenvalues. Let's see, this actually does factor nicely. Right? This can factor as lambda. Let's see, we want two numbers that multiply together to give us 0.6 and add together to give us negative 1.6. That'll be lambda minus 1 and lambda minus 0.6. Therefore, we get our two eigenvalues. Lambda could be either 1 or 0.6. And as we'll see, in these problems, we're going to actually expect to have one of the eigenvalues equal 1. We're going to probably expect the other eigenvalue to be a number less than 1. All right, so let's continue on. And so recalling that our matrix for migration was 0.9, 0.3, 0.1, and 0.7. And we have the eigenvalues. Maybe I'll write them as lambda equals 1. And I'll give the other one a different name later. And I'd like to find the eigenvectors associated to each of these eigenvalues. So you might recall that the eigenvector eigenvalue equation, I have m minus lambda I times the eigenvector v equals the 0 vector. And so I'll write this as 0.9 minus 1, 0.3, 0.1, and 0.7 minus 1 times this eigenvector, v1, v2, equals the 0 vector. I'll turn that into a system of equations, which we'll expect to be redundant. 0.9 minus 1 is negative 0.1 times V1 plus 0.3 times V2 equals 0. And then 0.1 times V1 minus 0.3 times V2 equals 0. Sure enough, we do have a redundant set of equations here. So we'll pick some simple values for V1 and V2, which make these work. V1, we can think of that as our free variable. So maybe I'll set V1 equal to 3, in which case V2 equals 1 will give us a solution to this equation, to both of these equations, which means that our eigenvector V is 3, 1. Similarly, I'd like to calculate an eigenvector for the second eigenvalue. Maybe I'll call that kappa. That was 0.6. All right, so once again, I've got the equation m minus my eigenvalue times I times the associated eigenvector gives us a 0 vector. So same equation as before. Let's see, I have 0.9 minus 0.6, 0.3, 0.1, and 0.7 minus 0.6 times W1, W2 equals 0, 0. Again, let's convert to a system of equations. This is going to be, let me write this as 0.3 times V1 plus 0.3 times V2 equals 0. Sorry, those are actually, those should be W's. Let me go ahead and change those into W's to be consistent. And this should be W1 and W2. I'm writing 0 point just because I'm always worried about losing a decimal point, and if I have room, it's really better mathematical style to write 0 point something than just point something. All right, similarly for the second equation, that will become 0.1 times W1 plus 0.1 times W2 equals 0. And so again, we've got a redundant system of equations, so we have a free variable. Let's pick W1 equals 1. That means W2, to satisfy both of these equations, we would have to choose that to be negative 1. And so our next eigenvector is 1, negative 1. Excellent. So far, we have our two eigenvalues, 1 and 0.6. We have the associated eigenvectors 3, 1, 1, negative 1. Now previously, we learned about something called diagonalization, which means we can write any matrix A, or in this case, we called our matrix M. We can write that in the form P times D times P inverse, where P is a matrix of eigenvectors and a D is a diagonal matrix of eigenvalues. Right, so we can write this where D, again, that's going to be equal to our eigenvalue matrix, and P is our eigenvector matrix, where the eigenvectors form the columns. And so where lambda and W, sorry, not lambda and W, but lambda and kappa are eigenvalues, and V and W are the corresponding eigenvectors. And the reason this is such a useful fact, one potential application is calculating powers of a matrix in a computationally nice way. So m to the nth power would be P times D to the nth power times P inverse. And the way you can see that is by writing out P times D times P inverse next to itself. And notice that a lot of P and P inverses will cancel from the middle portion of that expression, leaving you with the diagonal matrix D to the nth power. All right, so we have our values from before. We have, let's see, our eigenvalues. Let's go back a slide. And our eigenvalues are 1 and 0.6. Our eigenvectors are 3, 1, and 1, negative 1. And so D is going to be 1, 0, 0, 0.6. Then P, which contains the eigenvectors, the first eigenvector was 3, 1. The second eigenvector was 1, negative 1. We also need to calculate P inverse using the formula for the determinant of a 2 by 2 matrix, AD minus BC. So that's going to be negative 3 minus 1. So that's negative 4. So we have negative 1/4 times the matrix, swapping the diagonal entries, a negative 1 and a 3, then negating the off-diagonal entries. There we go. And if we so wish, we could write this as a quarter, a quarter, a quarter, and negative 3/4. And now we can put this into our formula for our population matrix, or our population model. Right? Remember P to the power P of T, the population at time T. Think of that as M to the power T times the population at time 0. Right? But here, because we know we can diagonalize our matrix, we can also write this as P times D to the T times P inverse times the population at time 0. And here I'm using trying to use a lowercase p for the population at time t function and a capital P for the eigenvector matrix. All right, and the long-term population, remember, long-term population, right, in that calculation, we're going to let t get really large. We're going to let t approach infinity. So what happens to d to the t? Right, d to the t, calculating power of a diagonal matrix is pretty straightforward. We just calculate the powers of the diagonal entries. So we have 1 to the t, 0, 0, then 0.6 to the t. Well, 1 to any power is still equal to 1, and a number less than 1, raising it to a large power makes that smaller and smaller. So this matrix actually will become the matrix 1, 0, 0, 0 in the limit. And that's going to give us a pretty nice long-term population formula. And so the limit of the population as time goes to infinity of P of t, that's going to be equal to the matrix P. Right? And actually, let's replace that with the actual matrix P, which we know. Right? That's the matrix of eigenvectors. So 3, 1, 1, negative 1. 3, 1, 1, negative 1. Times 1, 0, 0, 0. Times 1/4, 1/4, 1/4, and negative 3/4 times the initial population distribution. In this case, 60, 80. All right, let's go ahead. I'm going to multiply from left to right. So multiplying these first two matrices together, and all the 1s and 0s is going to make this relatively straightforward. Let's say I've got 3, 1, dot with 1, 0, give us 3, 3, 1, dot, 0, 0, 1, negative 1, and 1, 0. It's 1, 1, negative 1, 0, 0. Excellent. I'm going to drop these two down. So we've got 1/4, 1/4, 1/4, and -3/4. So again, I'll do some matrix multiplication. And we'll get, see, 30 times 1/4. So that'll give us 3/4. Then 30 times 1/4 -3/4. That'll again be 3/4. The bottom row, 10 times that will be 1/4. 10 times 1/4 -3/4. That'll be, again, 1/4. And notice that, again, as before, the columns actually, the values in the columns add up to 1. And so a nice, helpful check. And again, bringing down that vector for the initial population. So we have 60 times 80. And so finally, let's multiply together these two values. So 3/4 times 60 and 3/4 times 80. Right, that's going to be 3/4 60 plus 3/4 times 80. The bottom is 1/4 times 60 plus 1/4 times 80. Actually, something really interesting happens here. Right? Notice that we have the same number going across, so I can actually factor that out. 3/4 times 140, and then 1/4 times 140. Right? So if we do that calculation, 3/4 times 140, that gives us 105. 105. And then the remainder is 35. Right? 1/4 times 140 is 35. Again, a quick way to check that is that we do know that since this is a migration model, that the total population never changes. So notice that it still sums to 140. Kind of a nice, easy way to check. One thing I would like to call your attention to is that what if we had started with a different distribution between the two islands? Again, keeping the same population. So maybe I'll switch colors for this. So note that this only really depends, the long-term behavior only depends on the total population, not on the initial distribution of that population at time 0. Right? Even if you had changed the original populations to be something like, I don't know, 120 and 20 to be the population at time 0. Right? What happens in this case? Well, again, the limit, when time goes to infinity of the population, it's still going to turn out to be the same matrix, 3/4, 3/4, 1/4, 1/4, times 120 and 20. Right, and going through the same calculations, you're going to see that once again, we'll still get 3/4 times 140, and then 1/4 times 140. And so in this case, again, we get 105 and 35. Right, so the takeaway here, and I'll go ahead and write this on the next slide, is that in a migration model, in migration models, we've observed that the long-term population stabilizes. So long-term population stabilizes, or we could also say reaches some kind of an equilibrium. Reaches equilibrium. And it really only depends on the total population. Of course, the actual population in years 1 and year 2 and year 3, the population in individual years will heavily depend on the original population. But in the long term, it kind of evens out. You get to the same value in the end. All right, and those are migration models. We should go ahead and do another example, I think. It's always good to do more than one example. It's important to do lots of math because you learn math by doing math. All right, so for example, I'll go ahead and I'll make up some numbers here. I always like to draw a diagram. Let's see, I've got two regions, say region alpha and region beta. And I've got populations moving between them. Let's say maybe every year, maybe there's a lot of traffic. So maybe 50% of the population moves from alpha to beta. Let's say what percentage is moving in the other direction. 50% going one way. Let's say 40% going the other way. Right? Based on these numbers, given the assumption that the total population remains constant, that means that 50% of the population will stay in region alpha each year, and 60% of the population stays in region beta each year. We're going to create a mathematical model. Oh, one more piece of information we need before we can continue. Let's say the initial populations. The initial population. Let's say in region alpha you have, let's say maybe 200, and in region beta you have 300. And what we'd like to do is to set up a matrix model and to actually calculate or find the long-term population distribution. And in this example, even though we're using different numbers, we're going to notice that we'll have some of the same patterns appearing. The migration matrix, the columns will still add to 1. When we calculate eigenvalues and eigenvectors, we're going to expect one of those eigenvalues to equal 1, the other to be a number less than 1. And we will also, once we do the diagonalization, and the long term, we're going to expect to end up with a matrix whose rows are the same constant number. All right, so first, let's set up the model. The equation for the population at time t, it's going to be some matrix M times the population during the previous year. It's t minus 1. Right, so we'll think of it as, let's see, remember we're going from and to. From alpha and beta to regions alpha and beta. Right, from alpha to alpha, that's 0.5. From alpha to beta is also 0.5. From beta to alpha is 0.4. From beta to beta is 0.6. And so here, our migration matrix is 0.5, 0.5, 0.4, and 0.6. So our first step is going to be to calculate the eigenvalues and eigenvectors of this matrix, then diagonalize it, and finally figure out the long-term behavior. So M is 0.5, 0.5, 0.4, and 0.6. Is that right? That's right. And so again, to find the eigenvalues, we want to solve determinant of m minus lambda times I is equal to 0. See, I'll have 0.5 minus lambda, 0.4, 0.5, and 0.6 minus lambda. And the determinant of this will be equal to 0.5 minus lambda, 0.6 minus lambda, minus 0.5 times 0.4. Here, let's see, 0.5 times 0.6 is going to be 0.3 minus 0.5 lambda minus 0.6 lambda plus lambda squared minus 0.2. Let's gather like terms. We'll have lambda squared. See, these constants combine to minus 1.1 lambda, then 0.3 and minus 0.2 add up to be 0.1. If we set that polynomial equal to 0, this factors rather nicely into lambda minus 1 and lambda minus 0.1, from which we know our eigenvalues are 1, as expected, and 0.1, a number less than 1, as expected. So those are the eigenvalues. Next, we're going to calculate the eigenvectors. All right, so next page. Again, as a helpful reminder, the matrix is 0.5, 0.5, 0.4, 0.6. Let's first do the eigenvalue lambda equals 1. Remember, we're solving m minus lambda times I times the eigenvector v equals the 0 vector. So the equation here is 0.5 minus 1, 0.4, 0.5, and 0.6 minus 1 times the eigenvector v1, v2 is equal to the 0 vector. Let's convert that to a system of equations. See, 0.5 minus 1, that should be negative 0.5. So negative 0.5 times v1 plus 0.4 times v2 is equal to 0. The second equation, 0.5 times v1 minus 0.4 times v2 equals 0. All right, so I need to pick some values for v1 and v2, which will make this not too bad to solve. Let's see. Maybe I want to make v1. See, I'd like to avoid decimals whenever possible. See, maybe I'll make this 20. Because 20 times negative 0.5 will be negative 4. Right? And then, wait a second, no, it won't. I'm just getting the numbers jumbled up in my head. If I make v1 equal to 20, then v2 equal to 25, that should work out. Because negative 1/2 times 20 is negative 10. And then 0.4 times 25, it's like 2/5 times 25, which is also 10. All right, so I think this is going to be, seems like large numbers, but I think this is one of the smaller eigenvectors with integer numbers. Let's do 20 and 25. There's our first eigenvector. Now let's do the other eigenvalue. And so reminding ourselves of what this is. Whoops. Reminding ourselves of what this is. We have 0.1 as our other eigenvalue. So this is kappa equals 0.1. Again, for this second part, we need to calculate m minus kappa times I times w equals 0. W is our new eigenvector. So I'll have 0.5 minus 0.1, 0.4, 0.5, and 0.6 minus 0.1 times our eigenvector w1, w2 equals the 0 vector. And here, let's see, 0.5 minus 0.1, that's 0.4 times w1 plus 0.4 times w2 equals 0. For the second equation, we get 0.5 times w1 plus 0.5 times w2 equals 0. So once again, these are nice redundant equations. Let's pick for w1, let's pick perhaps 1. And then for w2, let's pick -1. We have to pick -1 so that these equations work out. So our next eigenvector is 1, -1. Right, so we've got our two eigenvectors corresponding to our two eigenvalues. Now let's use this to diagonalize the migration matrix M. And so we can write M as P times D times P inverse, where P contains the eigenvectors, so 20, 25, 1, and -1. D contains the eigenvalues along the diagonal, so 1, 0, 0, 0.1, and P inverse. Let's see, we're going to have -20 minus 25. So -20 minus 25 will be -1 over 45 times -1, 20, -1, and -25. And so we could simplify this a bit. 1 over 45, 1 over 45, then 25 over 45. So again, that should reduce as well. And 20 over 45. And reducing these fractions to make our lives easier. 1 over 45, 1 over 45. 25 and 45 are both divisible by 5. That's 5/9 and 4/9. All right, we're interested in the long-term population distribution. We know what the long-term total population is going to be. That stays as a constant. And so we're interested in the limit as t goes to infinity, the population at time t, right? That's going to be equal to p times d to the tth power times p inverse times the original population at time 0. And if we were to calculate the tth power of the matrix D, and remember to do that, we just have to calculate each one of those numbers to the tth power. Just like before, we're going to have 1 to the tth power equal to 1, and a small positive number raised to the tth power is 0. And so to calculate this, we need to calculate 21, 25, -1 times the matrix 1, 0, 0, 0 times this fractional matrix 1 over 45, 1 over 45, 5/9, 4/9 times the original population distribution. I think that was that 200, 300? Let's go back and check. Yes, 200 and 300. In the end, we're going to expect that once we multiply the three matrices out, we're going to get a matrix where in each row we have the same number appearing, which means that the long-term population distribution will only depend on the total population, not the initial distribution. Right, multiplying together these first two matrices. You'll have all the ones and zeros there. So I'll have 20, 0, 25, and 0. Next, I'll bring down this matrix of 1 over 45, 1 over 45, 5 over 9, and 4 over 9. And let's multiply this out. Let's see. First, we'll get 20 over 45. It's going to reduce nicely. And 20 over 45. See, along the bottom row, we're going to get 25 over 45, 25 over 45. And again, the columns sum to 1, as we would expect. And so we could, let's see. So I'll have to carry down the 200, 300 for each one of these. Then carrying this calculation over here, see 20 over 45. That should simplify nicely, right? We can divide the top and the bottom by 5. So that gives us 4/9 times 200 plus 300. And then 5/9 times 200 plus 5/9 times 300. So I'm factoring out the ninths right away. Make my vector a little bit more nicely sized. Right, so I'll have 4/9 times 500. Let's see, does that simplify to give us anything nice? 500 times 4/9. Nope, it does not. This is equal to 222 point, repeating 2, and then 5/9 times 500. And that'll be 277 with a repeating 7. So we've got that division by 9 there. So this is the long-term distribution. We get about 222 birds or other individuals of our population in region alpha, and about 278 in the other region. And if you wanted to, there's always ways to check your mathematics, but you could try calculating, just as a practice for multiplication, try calculating the first few years of populations. So this isn't a full check, but try in this case. What is population in year 1? So find population in year 1, population in year 2, just by hand. Calculate the migration matrix times the original population, and it should be getting closer. It should start to approach the values we found for the long-term population. All right, thanks for listening.